Hi everyone, how are you? We'll start in a minute, so check out your notes and assignments. We're going to go over chapter 9 today. Okay, I'll go ahead and get started. Hopefully people will be able to join us. So for this week, we are going to go over Amdahl's law. And since we've been talking about parallel programming in the last couple of weeks, we touched on concurrent in the prior week. So this week, we're going to look at Amdahl's law and how it can be applied to really measure speed up for your program in case you need to do analysis. So in this chapter, it starts with talking about how sequential programming compared to parallel programming, and we can look at parallelizing as a way to optimize or speed up our program. And we need to be able to measure it to see what the speed up would be, how the performance would be improved. So when we look at concurrent and parallelism, we would think about the different approaches. Normally, you would see that the developers, they would either choose to have a pool of thread or a pool of processes, as we covered in the last couple of weeks. And we want to look at how we can significantly improve our program based on the measured execution time. So if we are writing a sequential program and we convert that, or we improve the program to be parallel, then we have to see how that program has improved, right? We want to be able to measure the time and compare the time. So Amdahl's law is a way that we can look at parallel computing and to be able to predict how the program has improved. And so you're really looking at the speed up by using multiprocessor. Just like last week, we were writing multiple programs to utilize the pool processes or workers. So in the example here, what you would see is that if a program needs 20 hours to complete a single thread, then we can look at the 1 hour as a fraction of that program cannot be parallelized. So that means that we would mostly be able to implement parallelism, usually not at 100%, but close to 100%. So in this case, what you would see is that 19 out of the 20 hours of the execution time can be parallelized. So the small fraction that cannot be parallelized, right, would not be hugely impacted, as we would mostly improve the program through parallelizing. So when we measure this, we would look at how the speed up would be based on the limitation. So it tells you here that the minimum of time cannot be less than 1 hour. So the minimum execution time cannot be less than 1 hour. We know that if we start out with 20 hours for the execution time, if we are able to parallel 19 hours, right, the rest is going to be, the difference is going to be the 1 hour that cannot be parallelized. So when we apply this into the equation, we look at the thread performance. So you would take 1 divided by 1 minus P, where P is going to be 0.95 or 95%. And that's going to be equal to the number of hours that we need to execute for that program. So based on Amdahl's law, we can look at the speed up in the latency resulting in the execution task. So the speed of the program is going to be the time that it takes to execute the program in full. And in the example, that will be 20 hours. The speed up is going to be the benefit of executing the program with parallelizing. So if you are able to improve 19 hours out of the 20 with parallel, then we can predict the speed up for the program. So in the below part, it talks about the time for the program to execute in serial. That means one processor. That's going to be divided by the time that it takes to execute in parallel with multiprocessor. So you would have T of 1 divided by T of J, where J could be the multiple processors. So T of J is the time to execute using a certain number of processors. So if you have 4 core, right, that will be 4 processors. If you have 8 cores, the J would be 8. So we can assume that we can create nth number of workers. So that will be n to be fully parallelized. So let's say that if we can create 8 workers for 8 processor, each one is going to be divided up for 1 task. So the job can be divided equally to n. And so with that, the number of workers can work together to complete the job faster. So that means that we can take 1 divided by n for the number of time that it takes 1 worker to complete the same job. Now, as we mentioned earlier, based on this theory, the application for this theory, note that we cannot parallelize 100%. So you will have some part of your program, depending on the program, that will be sequential, meaning that that's the traditional, right, Python that we can only execute top to bottom. So in your overall program there, the parts that are parallelized, we can utilize that part and apply Amdahl's law to measure the speed up. So for our first question, let me come back to the top. For number 1, it asks you, based on Amdahl's law, what is the program speed and speed up? So we can say that the speed of the program denotes the time that it takes for the program to execute in full. So the entire program execution. And this can be measured in the increment of time. So we can say that it could be 20 hours or it could be 20 seconds, depending on the program. So the entire program speed, that will be the time that it takes for the program to run completely. The speed up is the measurement of the execution in parallel. So that will be the time that it takes for the program to execute in serial divided by the time that it takes for the program to execute in parallel, as the program would have both parallel and serial parts. So it is the ratio of sequential execution time to the parallel execution time. So you would need to measure the part that is serial, and that will be divided by the execution time for the parts that are parallel. And we would use the equation today to really predict the type of execution time, or the execution time for our program, based on number of processors, based on the improvement. Any question regarding number 1? You can find this information on the first page of your notes, and you don't have to put it verbatim, but I want you to understand the difference between speed and speed up. So as we look at Amdahl's law here, the equation is provided here on page 1, and we're going to break it apart and see what each part means. So the formula is really used to estimate the speed up in the parallel program. And so we can make a prediction of how fast the program will be running in parallel. So that means that we would take B times T of 1, which is the time that it takes to execute the part that is sequential, the part of your program that is not parallel. So that will be your B times T of 1, this part right here. Then the second part, which is to its right, you're going to take T of 1 minus B times T of 1 equal to 1 minus B times T of 1. This is going to allow us to produce the result of time that it takes to execute the program in parallel. So for this part right here, okay, in implementing the fraction, so you would take T of 1. So this part on the right is going to be the ratio for the parallel compared to the measurement for sequential. And we would add those, so we would find the sum. Then we would take the time, T of 1, which is going to be 1, divided by the sum of both. Okay. So when you have 1 minus B times T of 1 divided by N, this is going to be the time that it takes to execute the parts with a certain number of processors. So if you have 4 cores, right, that will be the measurement of your 4-core time to execute the program. And then when we apply the entire program, so when you take B times T of 1 plus 1 minus B times T of 1 divided by N, this is going to give you the total time that it takes to execute the program with a certain number of processors. So if you have 8 core, this is going to give you the time that it takes for the 8 core to execute your entire program. And that is different than the previous bullets, because the previous bullet states that this is the execution time with a certain number of processors. Okay. So if we look at this example, if we say that our program has 40% that is parallelized. So what you would start to find B is you would take 1, which is 100%, minus 40%, which gives you 60%, or 0.6. And that 0.6 indicates that it is sequential. 60% of our program is going to be sequential. That's not parallel. Then for the parallel parts, if we are using 4 core or 4 processor, our J is going to be 4. So when we apply this to Amdahl's formula, we can plug in 1 divided by B, which is at this point 0.6 for the example, plus 1 minus B, which is 1 minus 0.6 again, divided by J, which is 4. So this is what you see right here. And when we put that into our calculator, we would have 10 divided by 7, which gives you 1.43. And so this gives us the speed up measurement for parallel implementation in our program, which is the 40% of our program. Okay. And again, this is going to be the estimate. So you won't have the exact value, right? It is a prediction. So it's just a way for us to have an idea of our execution time with Amdahl, with parallel using Amdahl's equation. And so I included the quotes here. So what we can see is that this is a way, it's a technique for us to look at whether we can improve based on parallel implementation. So when you have the sequential portion of your program, it's going to be the overhead portion that's required for the program. That is going to be the upper boundary on how your speed up would be. And so the speed up, we would look at the number of processor and how it would improve or gain based on the number of processor compared to only a single processor or a serial processor. So we would see that as the number of processor increases, the speed of execution of the whole task also increases. That doesn't always mean that we should implement concurrent programming, because there is a level of plateau at one point where you would reach and it won't be able to improve any further. So what you have to think about is whether concurrent program is applicable in the implementation or parallel is applicable using multiprocessor for your implementation. And it is important to really understand that you don't always implement parallel or concurrent programming to achieve the highest possible performance. But it is an option, and it doesn't always mean that there is improvement. And we saw that in the when you run multiprocessors or worker pools last week, right? You see that sometimes it takes a little longer or even equivalent, or it doesn't really save much time at all. So does it really mean that when we add more processor, that's going to help the improvement? So as the experiment and researcher has implemented this, what you would see is when you add more processor to a concurrent program, eventually you would obtain less improvement in execution time, right? Because remember that your program is not fully 100% parallel, but even when you add in, so let's say that I increase the core values, and we assume that that might improve our program, but it doesn't necessarily mean so. And so based on that, when you take a look at this, right, you would see that your execution time doesn't always improve with more processors. Okay. So this is a chart that I grabbed. So what you can see is when we look at the parallel portion in this example, that will be 50%. That's in blue, solid blue here. And as we look through, and if we keep increasing the processor at one point, about 20 or so, right? What you can see is it's then gonna improve and then it's gonna plateau. So your speed up about 20 is gonna be the maximum. So that's gonna be the limitation. Then if we parallelize 75%, you don't really see a huge improvement compared to 95%. Okay. Or if we parallelize 90%, but as you look at the number of processor as we increase that, right here is where you see the draw. Okay, so it's going to plateau after that. So even if we increment it by thousands, you don't see a huge difference in that. Okay, so for 2, it asks you, what does the program's efficiency speedup divided by the number of parallel processor calculation provide? The program efficiency describe how well the parallelized or the parallel processing resources are being utilized, such as the number of cores, right? So when you refer to program efficiency, it's really the speedup divided by the number of parallel processors. And that calculation shows us how the resources are being utilized for parallelism. So with that, we can calculate a program that is 70% parallelized and you're using an 8-core processor. So when we apply it with Amdahl's equation, we can estimate the speedup for the program. So first, you would need to find B. So you would take 1 minus 0.7 or 100% minus 70%, which gives you 30% or 0.3. And this 0.3 is the indication of the portion of the program that is sequential. So 30% of our program is sequential and 70% is parallelized. Then you can grab the formula from our notes and paste it so you don't have to type it, or you can do insert formula. So we need to calculate our speedup, which is S. So you would take 1 divided by B plus 1 minus B divided by J. So when we plug in the numbers, 1 divided by 0.3, which is the sequential, plus 1 minus 0.3, which is 0.7, that's the parallelized, divided by 8, which is our core values. So we can see it is roughly 2.58 times faster. Now, then we can make adjustment to our program. We can say, what if I parallelize 90% of the program with the 8-core? What would that look like? Okay. So, or we can look at, if we increase the core, would that make a difference? Right? Based on the graph, you can see that it does increase until it reaches a certain point with the number of processors. So this is how we can calculate the estimate of the speedup using Amdahl's law. Any question? So for final exam and quiz, make sure that you know how to apply Amdahl's law for speedup and what Amdahl's laws consist of. Then for question 4, it asks you, when implemented concurrent and parallel techniques, what is the upper boundary on how much speed up the program will gain? So the sequential nature of the overhead portion required by the program always set the upper boundary. So the portion of your program that is sequential is going to set up the upper boundary on how much speed up the program will gain. And the overall program is reliant on that, as it requires the overhead for the sequential part to run. And so that will be your upper limit. Any question? Okay, so again, you can find this on our notes. And then for 5, we would just rephrase kind of number 4 content. So for 5, it asks you, what is provided in using Amdahl's law calculation of the overall speed up that parallelize the program? So that will be your program upper limit. Okay. So now let's come back to here. So that will bring us to the relationship and how this relates to the law of diminishing returns. And so the law of the diminishing returns is the only special case of applying Amdahl's law. And when we look at the improvement, we have to really think about how the task is implemented in our program. And so it tells you here that in order to separate the tasks in the program and the chosen to be improved in an optimal way, you would see the decreasing in improvement for the execution time. And that shows the diminishing returns. So the optimal method would be applying the improvements that will result the greatest speed up and leaving those improvement yielding smaller speed up for later. So that means that when you design the program, you have to think about how we can implement optimal method where the major of your improvements is going to be yielding the greatest speed up, and that is earlier on in the program. And so if we reverse it, it will improve less. So if you have slow start, right, faster portion in the later part of your program, you're going to have the reverse sequence, which is going to not be the optimal method. So it is more beneficial for us to really think about the order of your optimal method. So when you improve your program or your system, and if you use the reverse optimal order, the optimal components are usually more complex, and that takes more time to improve. So hence you can see that there is a relationship between Amdahl's law and law of the diminishing return in the area of improvement of speed up. And so in Amdahl's law, we saw that as we increase number of processor, right, to a certain limit, of course, right, we would see some improvement. And if we draw that relationship and bring that into the implementation of your optimal method, we want to really think about how you can greatly improve the speed up by handling the complex task with the parallel. And so we would then apply the reverse optimal order. So coming back to the assignment now, right, we can answer number 6. Based on Amdahl's law, how many cores can be implemented for the program that is 95% parallelized and 50% parallelized? So you can look at the graph on the notes. Okay. Right here. That's on page 3. And it shows you the number of processor here. So when you look at the 95%, which is in dashed green, when it hits 2048 cores, you would see some very gradual improvement or the same, no improvement. Now compare that to the 50%, which is in light blue down here. That is earlier on in the number of processors. So we can answer that a program that is 95% parallelized can have up to 2048 cores to achieve the approximate speed of 20 or speed up of 20. So if you want to achieve the speed up of 20, you can implement up to 2048 cores. Now, commercial PC that you see, most of the commercial processor that you see for personal use, right? We don't see that many cores, but you do see some higher, right, gaming system or processor that you can purchase that would have higher than 8 cores. You might find 12 cores or even higher than 12 cores. So when we parallelize 95% of our program, we can increase the number of cores to drive the speed up, or the increase of the speed up to 2048 cores. But if we only parallelize our program at 50%, your cores are ideal between 16 to 32 cores to achieve the speed up to. So as you can see, if the major of your program is parallelized, it would have direct relationship to the number of cores up to 2048. Whereas if you only have 50% of your program parallelized, you don't need to use that many cores, right? And your speed up is about two times. Okay. So beyond the 32 cores, you're gonna see that it actually is slower or the same. So we have a general idea on how we would be able to look at parallel as an option to create when we build our program or system. And we can also tie software into hardware as the hardware, which is your processor, right? The number of cores can be implemented to improve the performance. Okay. So it will be more beneficial if we parallelize the majority of the program if we want to maximize the use of our multi-core. And again, we cannot parallelize at 100%. There would be a small percentage or even half, right? That would be your upper limit or your sequential. Any question? Okay. So that would be the answer for 6. Then we touch a little bit on diminishing returns and your Amdahl's law. Number 7 asks you, how is Amdahl's law applied to the law of diminishing return? It's applied through using optimal method and reverse optimal order. We talked about how we would handle the complex area with parallelism, right? And an optimal method indicates first applying to those improvements that will result in the greatest speed up. and leaving those improvement yielding smaller speed up for later. So we want to handle the more speed up portion of our program. That means that if you are applying Amdahl's law, right, for parallelism, so we would handle the complex part and design our code to implement our parallelism for speed up at the beginning. And then the smaller part will be our sequential. So as more optimal components are usually more complex, that will take more time to improve, and improvement of speed up can be achieved by adding more processor to the system. So with that, you really want to have the optimal outcome. That means that you have to have more processor or multi-core for improvement. So we do see the correlation for the improvement between hardware and software, along with how the relationship of Amdahl's law to the law of diminishing returns. Any question? And so for number 7, you can refer to the section on the relationship with law of diminishing return on page 3. And so when you look at some of the example throughout your notes, and I also uploaded a zip folder on your notes page, and you can see some example there, and those example implemented threads. So it's a little bit different than using multiprocessing. And the program that you see on page 3 and 4, this is from an earlier chapter, but this program is using multiprocessing module, and it implemented features. So the program goal is to check for prime numbers, right? We would have math library to use square root, and then we would use concurrent features, multiprocessing module, like what we did last week, and then time it to measure the time. So we would have a function is prime, and we pass x. And we want to check if x is less than 2. If it is, return false. If it is 2, return x. If x mod 2 is 0, return false. And so we want the state limit is, and we parse it as an integer. We would take square root of x plus 1. After that, we would then implement a for range. And for our parameters, we would pass 3, limit, and 2. And within that, we would nest the if statement. If x mod I is 0, return false. Because when you check in prime, right, you want to make sure that you handle the conditions when it is 0. And then from the function, we're going to return x. Now, the second part of this is when we would implement worker pools. So you do see that this part is sequential, right? It's just going to go and check the conditions as x is entered or hard-coded in. Now for the concurrent part, we would have concurrent solve, that is our function. And for our parameter, we would use n workers. We would then display the number of workers that we're using. We start the clock. The result is a list. We're going to append it as we go through. So to really handle the multitask with multiprocessor, what you can do is you would be able to have a storage location where it's going to append the result. Then you would set up your pool. And so the max number of workers is going to be your N workers as an executor. And we talked a little bit about executor last week. And then below that, we would implement lists for features. So we would have the executor, it's going to submit for is prime. So this is where you call the function is prime from the top, and then you would loop it through. So once that is set up for your futures list, then you would use it as a parameter to set up the completed futures. So here you would use as completed for the futures. And then you would have another timer start. So that allows us to implement the time as each of the process or each of the worker executes. Then the next loop is going to be using the completed futures. So it's going to check to see if there's the result. If there's result, it's going to append to the result list. And then we find the actual time by doing the subtraction for both parts, the duration of the entire program, the duration for our processors to handle the task. And then we would print the time output. And here is where your input comes in, because earlier we state that, there's X, and then so we would need to be able to loop. So your input is going to be a list, and within that list, we're going to implement the for loop and pass the values. And then for here, this is simply to do your processor count. And as we move through multi-processors, we have to increment. And then we would call our function concurrent solve and its parameter. And then we will print. So to utilize a program and implement parallelism using processor pool, you do see that this program itself has the sequential portion, has the parallel portion. Once you yield the time, right, and we can even implement the time as we see at the top, okay? So if you measure the time for just the sequential part, and you look at the time, the overall time for the entire program to run, or the time for the parallel compared to the entire program execution time, you will be able to find the percentage. And based on that percentage, you can use Amdahl's law to be able to calculate the estimate of your speed up. Okay. So here it tells you that the concurrent program is a mixture of both parallel and sequential. And so when you use Amdahl's law for analysis, you can find how the speed up would be through the number of cores. So that's why we increment right here. And we want to be able to test with possible speed up for parallelization. So the trade-off between the number of processor versus the increase of how long parallelism is applied, because it does take a little longer, but we're able to shave off time. using more processors. So you do have a trade-off. Now, if the program is 40% parallelized, that means that when you're using multi-core, they are simultaneously working on that 40% of the program that is parallelized. So that means that we can look at how the task is increasing the speed. So if we are using 4 processor to execute the time, this is the speed up, 1.43 at 40% parallelized, right? You take 1 minus 0.4, you get a 0.6, which is your sequential, and then you plug that in with the number of core. So that will be 10/7 or 1.43. But if we reduce the number of processor, if we only have 2 core implemented, right? And we plug that in, this is incorrect right here. So let me recalculate this. I just cut this. So you would have 0.6, 1 minus 0.6 because it's 40%. So that would be 1 divided by so let's see, divided by 2 plus 0.6 equals, and then we would take a fraction of that. And so that will be 0.07. So 1 divided by that. That's not right. Point 4 divided by 2. And take a fraction. So it's 1.25. Okay. So the speed up for this with the 2 core at 60%. Okay. So you do see that sometimes when you increase the processor with the certain percentage for parallelized, it doesn't always mean that you would have the increase in performance. But in this case, we see the increasing in speed with the increasing in the number of processor. So your speed up is 1.43, which is higher than the speed up of 1.25 with dual core. So it is faster using 4 core compared to dual core. Okay. Now we can also alter this. So if we want to increase the core here to 8 or 10 or 12 or however many cores that you want to implement, and we can look at the estimate for the speed up. Any question? Okay, so now let's handle the next question, number 8. True or false? Increase the number of processor with the fixed problem size per processor leverages weak scaling to accomplish more work in less time. That is false. If you increase the number of processor with the fixed problem size per processor leverages weak scaling to accomplish more work in the same amount of time, not less. So when we look at the measurement from that last program, we would see that when you go from dual core to quad core, the overall execution, because your upper limit is reliant on the 60% that is sequential, right? So when you're using weak scaling, it's only going to be operable with the number of processor it is handling at the same amount of time. Now, because when we look at Amdahl's law, the overhead is not going to be accounted for in parallelism for certain things. Like you have to consider the factor that, you know, memory access speed could be varied. Okay, because your data is actually stored in a certain location, and how fast it can access data can be a factor. And also your overhead in parallelism, because when you have the increased number of processor, that will be increased in the amount of time that it would take for execution. Okay. Assuming that even if we're looking at the same percentage of parallelism, it doesn't always necessarily mean that it would be faster. There are other things that we also need to consider. Okay. So here it is an estimate. And so when we optimize the concurrent program, if we look at the number of available processor, it won't be precise. It would only be an estimate of the speedup. So it is a good way to really plan and think about how you would design or redesign your program for improvement using parallel and concurrent programming. Okay. So for 9, it asks you what is the trade-off in achieving the best possible speedup and parallelization. So the trade-off is if we increase the number of processor versus we increase how long it would take to execute parallel portion of our program. And for 10, it asks you, since Amdahl's law does not consider the overhead of parallelism in or speed of memory, why is the law used in programming? Because it gives you an idea about where and how much we can optimize our concurrent system, like looking at the number of available processor for implementation. So it is a way for us to identify theoretical strategies in improving computing speed using concurrency and parallelism. Okay. So when you consider those options, because you can write your program and your program doesn't have to be 95% parallelized. We can have 50%, we can have 20%, but it is a good way for us to have an estimate or a general idea of how the performance would be, whether it's improved or not. Okay. So in practice, now that you know how to apply the equation, we would work on applying this concept in our Python programming, right, for our lab this week. So since it's pretty early in the session, I also want to go over some of the example. And the example is actually pulled from a module that was applied in LinkedIn Learning. There are a few lessons in there that were pretty good, right? So So if you need access to LinkedIn Learning, let me know. I can add you and you'll be able to access some of the module on there. And as you complete them, you can earn badges on LinkedIn. Okay, so let's take a look. And I uploaded the zip file. So if you want to run the program, and remember it's Python 2, close to Python 3. So, and these uses concurrency versus parallelism, because you're going to see that it uses threads instead of multiprocessing. Okay. So when you unzip your program, it's going to look like this, and there are various chapters. So in that, you would see like different types of program. So let's take this program, for example, because the other ones are kind of simple and implement. So this one uses multiprocessing. And this one shows you how you can do matrix multiplication. I think we talked about that when we hit on the array and multidimensional array, how to be able to apply matrix, and we talked about shaping. So to implement parallelism in a program like this, right? Simply you would have your libraries, and here they use multiprocessing. And we're going to have some math operations. So we'll bring in the math module, and we want to measure time. So you have a function called sequence matrix multiply, and we're going to pass AB. Then you would establish the variables that would represent your columns and rows, right? Because you're going to do A by B as the multiplication. So the variable num rows A is going to hold the length of A, and then num cols A is going to hold the length of A, starting at the index 0. So that this is going to be your rows A and your column A. And we want to multiply that across with B. So then you have the variable for row B and columns B. Now we want them to be equal in length, as we want to make sure that the dimension can be applied for multiplication. So we don't have to reshape before. So you would have the statement to check to make sure that it is the same in columns and rows for both A and B. And if it is not the same in size as a matrix, you would have it raise arithmetic error. So the exception is going to be here, and you want it to notify. Then for C is going to be the container where we operate the multiplication. Okay. And we would need to loop through rows and columns. Columns and rows for B to A. Then for rows A, we would also nest another for loop for the columns B. And then for columns A, we would be able to handle. And so you would simply use the indices and increment the indices as you go across rows with column in multiplication between A and B. And you would return C as it would store your result for that part from the function. Then the second part is going to be your parallel. Similar to the sequential. So this is the sequential part of the program. This is the parallel part of the program. You're still going to have to set up the matrix with rows and columns for A and B. And we would handle the exception when they are not exactly the same size as a matrix. And to practice, what you can do is you can establish a pool. Okay. So for this part, what we can do is we can bring in MP, which is for multiprocessing, and you can set up a pool of workers and increment through, very similar to what you've seen in the exercise in the for prime for the example. And then be able to access, right, A and B for multiplication. So you would then call on this method or function, which calls on this function. Okay. So in that, what you would see is when you handle the parallel part of the multiplication, it's going to be the bigger chunk in how it would call on this function, which is sequential. So in this case, the majority of your matrix multiplication is going to be implemented as parallel, whereas the sequential can also be used if you want to just have the overhead with the sequential. So that means that I can run this part of the program as a separate program, right? Or I can run this part of the program as a separate program. But in combination, what you can do is you can set up a pool and be able to access the other function. Okay. So in the main, you would have your A and B for the values as it is randomly generated. And then we would be able to print as it multiply. And it gives you the time. Okay. So the only area that you can practice in is to add the parallelism. Now, other example that you would see in the exercises file, let me come back here. If you start with like the simple one with threads, and you've seen this before where we would implement threading. So this, we're going to come back to threading again in the next couple of weeks when we talk about how we would be able to lock the thread. So here they had set up where you would have threading and you would have an object called slow cooker lid, and we would then lock the thread. And we would have a variable that's going to hold the value for our threads. Now, this example shows that you have 11 servings and you want to check for the number of people who are hungry. So we would globalize the servings and we would have a while loop while serving is greater than 0, which it is. It's going to apply the if. So if the person ID, we would take the soup serving mod 2 and the soup serving is greater than 0. And we would subtract it. So as you turn, right, we would take the soup. So we would give 1 soup per person. And then with that, we would do an else statement, else we're going to print. So show the person number, check if they put the lid back as they take the soup. And then in the main, you would say for I in range 2, we are going to have the thread. And this is going to target hungry person, which is your function, right? We saw this before. Your argument is going to be your index, and it's going to start each thread. This is going to be infinitely running because it's going to meet the condition for the while right here. Okay. So in this case, what you see is you would apply the condition variable, right? And so it's just going to keep starting the threads. And as it checked true, right here, it's going to go infinitely. We can stop this, right? And for the second part of the file, you can take a look at the end part. Okay. So the slight change from the last program to this, there is a wait implementation within the while statement. And then instead of mod 2, here you would implement mod 5. So because we want to be able to loop through 5. Okay. And then we also have like the notify all method implemented here. Okay, so this one, it does exit out of the loop, as you can see, because once it did not meet a certain condition as we decrease, right, it's gonna exit. So you can see that it would not be in order where we would have the thread, and it's just gonna call, and then it also set up a wait. So it sets up the thread 1 checked, then put the lid back, thread 3, thread 4, thread 2, and then it's gonna go to 0, then 0 checked, right? So you do see that it is concurrently working using threads. Okay. Unlike the last example that we saw, that when that was built, right, it just infinitely go. There's no decrement in how we subtract the number of people who obtain the soup. And so it never exits out of the loop. In this one, it does. At one point, right, it would be no longer greater than 0. So when you get to the later thread, when the last person took the soup, which is person 1, there's no more. So it's exiting out of the loop there. Okay. So this is how you can implement concur. And then what you can see is that if we apply concur for the majority part, we can set up the time to really measure how that program would run compared to a sequential program that would run. Okay, and then we would look at the overall percentage for the implementation and the number of core we're using. So on your computer, if you're using quad core, you can apply Amdahl to really look at the speed up between concurrent and sequential. Okay, so you can check out some of the example, look at how you can fill in some of the blank. I think some of the exercises have you fill in some of the code and see if you can do it to implement parallelism and then run the program. Okay. So there are other example. The majority at the beginning chapters, you're going to see that it's using threads. And then in the later chapter that you would see that it's using multiprocessor. So as you go through, this is one for measuring speed up. Okay. And this one, it creates a processor pool using processor pool executor. Okay, we saw this last week at the end of chapter 8. So you would have sequential function, you have the parallel, right? Then here's where you would set up your pool. Then it implemented features. And then, so it would check high or low, right? So your base case threshold is this. If high subtract low is less than or equal to this value, it's going to return and it's going to append that into the pool. Then else, right, we want to check if the middle index is splitting. So for the print, so let's see if we can run this. Let me see if it can spit out time. There we go. Okay, so when you run this program, and this program is from chapter 4, as you can see, to write a program that implemented both part and see the sequential time compared to parallel time. So you can see that in this program, the first part is the sequential, and then we have a function that will be parallel. Okay, and then we would implement the conditions and we would print. So it would evaluate the result and give out the time. So for the average time for the sequential, we would see that it is 5,278.5 milliseconds. And then for the average parallel time, it is less. So your speed up, right, that it would do the same thing with your Amdahl's law application here. That will be 2.04. The efficiency is going to be 25.51%. So this is a good example of how you can write your Python code, right, to measure the speed up and the efficiency, as we touch on that today. Okay, so look at measure speedup.py in chapter 4. Then for the end portion, you're going to see a similar example implementing, parts that are almost identical to the other one. Okay. And it is gonna, your threshold is less on this one. So we can take a look at how this is going to be applied. So it's going to evaluate the sequential. It's going to evaluate the parallel, just like the last one. And you can modify the program. So it might take a little bit to give you the output, but you can run the second part to kind of compare how the program would be. Okay, so on this one, which is the N, also the same name measures for your speed up, your sequential time is 4,276. Your average parallel time is 10,521. The speed up is not much. Okay, so my efficiency for the second program is only 5% compared to the first program, which is more. Okay. Okay, so it shows you how you can implement your processor pool and be able to do that. So I want you to check out some of the example programs, look at how it is written, and then how to be able to apply the measurement with the program so you can assess. Because for your project in the future, this will be helpful, or even, if you plan to implement parallel as a developer, you can apply, right, the techniques that's used in these example programs so that way you can test your program. Any questions? Okay, so we don't have that many questions in this exercise for chapter 9, only about 10. So what you're going to do is you can take a look at the lab for this week. Okay. And then let me talk a little bit about that. What I'm going to do is I'm going to open your projects, which is not due until the end of the semester, but I want to give you some time to kind of think about how you want to get started and then apply some of the concept that we are learning. So as you go through each week, right, you can think about the parts that you want to add to your project. Okay, so I will open that probably on Thursday, and so that way you would have about 6+ weeks to work on it. Okay. Let me see, I think it's the version 1. So we are going to do something similar to what you've seen in the example program. We're going to use the example program. We're going to run it. We're going to time it. And then we're going to look at the time, the speed up, and the efficiency. We're going to calculate or we're going to use multi-core in our virtual machine. So you can run it on your IDE as far as the lab, like what you've seen that I've used Tawny. And then we would use Amdahl's law to check, right, as far as the calculation for the efficiency. So the lab is not too lengthy either. If you want to implement it with your Ubuntu Linux, you can. So I will talk about the lab when we work on it on Thursday. So for this week, make sure that we go through the notes. Make sure that you look at your assignment. Make sure that you understand. And then take a look at some of the code, for example. And then let me know if you have any questions or concern. Okay. All right. Any questions? Okay, so I'm gonna stop. If you have any questions, I have to know. Okay, I see everybody's name here for attendance. Let me stop recording.